Hello and welcome to the ASU SIMS lab. It's behind me. I don't know if you can see it through that glass window. We'll take a tour there real quick. But what it's used for, and it'll be easier for me to describe it in this quieter room, is analyzing really tiny spots for just about every element in the periodic table and for several isotope ratios of these elements. We study minerals from meteorites. We've examined the solar wind from the Genesis mission. We study synthetic materials, experiments where people try to replicate natural conditions deep inside this and other planets. And these are really small samples from piston cylinder experiments, multiple anvil experiments, and diamond anvil cells. We do a lot of work with volcanic materials, minerals and glass from explosive and effusive volcanoes. We've looked at diamonds and the minerals trapped inside them. We also study minerals in low to high temperature rocks that aren't included in the ones I've mentioned so far. And we also studied quite a few photovoltaic cells, light emitting diodes, and other semiconductors. And overall, one of our other goals is to develop better ways of doing all those things I just mentioned. Now let's take a tour into the lab. Okay, now we're back. This is a secondary ion mass spectrometer. It's commercially available because the semiconductor business absolutely has to have these things because they dig a hole in a sample very slowly and monitor the chemistry with depth in the sample, so that if you have a set of integrated circuits that don't work right, you'd like to find out what layer went wrong. So what we do is we put the sample in an analysis chamber here and bombard it with energetic ions that are generated in one of two different ion sources. Today we're using the dual plasmatron. Ions for the dual plasmatron are accelerated this way, bent by a magnetic field. They go down this column and strike the sample in there at an angle of about 30 degrees to the sample normal. When the ions hit, they knock atoms off the surface of the sample, and those ions are accelerated away from the sample, which is held at a high voltage also. The ions go through an electrostatic analyzer. They get weighed in this magnet here, and an isotopically pure beam comes out this part of the instrument, and we either take a picture of it with our camera here, or else we send it into a counting system and a count rate for the trace element. Here you can see the light microscope image of a sample. It's an aluminum plate with a copper screen or grid squished onto it. And when we turn off that camera and let the ions hit it, we see is a chemical map. I'm letting only aluminum ions hit our detector, and I said it's an aluminum plate with copper screen on top. Well, wherever it's bright, there's lots of aluminum. Now, what I'm going to do is decrease the current, because that's not a microbeam. By the way, each one of those squares is about 20 microns across, and if I turn down the current, I can take the spot down to, that's about a 3 micron spot. Now, let me go back. I can also change the field of view on it, just like having objective lenses in an optical microscope. Now if I turn the current down, there. Now I've got a beam that I can hide behind a 10 micron copper wire, almost. But this is something we can't do on the phone. All right. We are funded by the National Science Foundation to do analyses for earth science researchers, although we do let engineers in also. And we let students come in. We encourage students to run the instrument by themselves. This is where you would load different sample sizes into the sample mount and then put them in the vacuum chamber. This is an instrument that if you have skills on, you can actually get a job working for consulting firms or semiconductor firms. Thanks for your time.